Hi, welcome back. I hope you had a good weekend. This week I'd like to continue on chapter 4 on stratification. Very quickly, just a revision on why we perform stratification but not the simple random sampling. Let's say if we know that from the populations, we can easily divide the population into different strata, like different groups, and we also have a knowledge that within each of the stratum, the characteristics is quite similar to each other, and between strata they're quite different. So let's say we would say within a stratum they are homogeneous, between strata they're heterogeneous. If this is the case, we can perform stratification rather than simple random sample, because under stratification we can have a better estimate of the point estimate, like the y-bar, proportion, or total, and as a result we would have a smaller estimated variance for my point estimate. A smaller estimated variance would result as we could have a smaller margins of error. A smaller margins of error, that means with our 95% confidence interval, we can have a better conclusion with our point estimate. So that could be a better estimation or a better estimator for the population. Okay, so again, under the stratification, last week we also discussed about how we determine the sample size and also how we allocate our sample size n into each of these stratum. Okay, all right. So this week I like to move on to the technique that we learned from chapter 3, that we can make use of some of the auxiliary information, let's say x, in support of us to estimate y variable. So we know that x and y, they perform a linear relationship, then we can do a ratio estimation and also a regression estimation. Okay, so I like to combine the both of them. Let's look at my handwritten notes. Okay, so in chapter 3, under the simple random sample, we learned the ratio estimation. Ratio estimation is saying that we know x and y, they exhibit a linear relationship. Then we can look at the sample y bar divided by the sample x bar. Then we can estimate R, which is a ratio. A ratio, we can make use of this ratio to be an unbiased estimator for the population ratio. That means if I use this R multiply to the true population x bar, then I can estimate the true y bar for the population. So this is the y bar under ratio estimation. And the estimated variance for my y bar under ratio estimation is equals to SR squared divided by n multiplied to the finite population correction factor. SR squared was defined as SY squared minus 2R SXY plus R squared SX squared. So again, under the ratio estimation, the variance of my point estimate y bar would depend not only on SY squared, not only on the sample variance of y, but also on the variance of x and also the covariance part. Okay, so this is what we did in chapter 3. Chapter 4, stratification. We divide the population into different strata. Within the stratum, we estimate y bar, and then we add up all of the y bar for each of the strata, add them up weighted by their population ratio or population fraction. Okay, so this is my y bar under stratified random sampling, and the estimated variance equals to each of the estimated variance for each of the stratum, adding up, weighted by the again the population fractions square. Okay, so this is how we do for the stratification. Let's combine both of the methods A and B, stratification and ratio estimation. So if I divide the population into 3 strata, let's say, then I can look at stratum 1. I estimate y bar for this stratum using ratio estimation. I estimate y bar 2 using a ratio estimation. So that's for stratum 3. Okay, and again, within each of the stratum, I would rely on some of the additional information like the x value for each of them to help me to estimate my y bar. Add up all of the 3 y bar and weighted by the population weighted. So this is called the y bar overall estimate, overall population y bar under this ratio stratification. All right, so that's like I wrote it here. Stratum 1 rely on the sample y1 bar and sample y2 bar. We would have ratio 1. Stratum 2 we would have ratio 2, etc., etc. Okay, we call this the separate method. The separate method, that means we look at each of the stratum separately. Okay, and we have different R, called RL, for each of the stratum, and RL could be used as the unbiased estimator for each of the stratum through capital RL. That means I can estimate the stratum through YL bar using the ratio multiplied to the capital X bar L. Okay, so this is the true value for each of these stratum. My writing. So this is the sample X bar, little X bar, and this is capital X bar. Okay, so I use the ratio multiplied to the true X bar L for each of the stratum, then estimate the YL bar. Then after I estimate each of the YL bar, I add them up under the stratification method, right? So I add up by the omega, the capital W as the weighting. Again, the estimated variance for my y bar under ratio and separate methods is equals to the estimated variance adding up together weighted by the capital WL square. Okay, estimated variance would equals to the SL square divided by sample size multiplied to the final population correction factor, and the SL square, same as before, that equals to the sample variance square plus the sample variance of X square, also taking into account for the covariance part. And all of the R would be different for each of the stratum when we do the calculation. Okay, so that we need to add up 3 of them if we have 3 strata. The second method is called the combined method. Okay, so combined method, we first apply stratification techniques. So that means if I collect the sample y bar, I add them up together weighted by the population fraction, then I would have y bar under stratified random sampling. I add up all of the sample X bar, weighted. I can also estimate the X bar under stratification. Now I look at the ratio of them. Okay, the ratio of them becomes one constant, R. This is called R combined ratio. Okay, using this R, this is overall, then I can multiply to the overall true population X bar, then to estimate my Y bar for the entire population. Under the estimated variance, again, we are adding up all of the estimated variance for each of the stratum, weighted by the population fraction square. Expand this, SL square in this case, again, will equals to the sample variance of Y, sample variance of X. We also have R. Under this, we would have constant R for the entire population. Okay, so under the combined method, we would have a constant R, whereas having the separate method, we would have different R. Okay, so we can choose to use different methods for ratio estimation under stratification. Which one is better than the other? Let's compare them. Under the separate method, think about that. We need to estimate each of the R for each of the strata, each of the stratum. So we require the knowledge of the true X bar for each of the stratum to find using the little r multiplied to the true value of capital X bar to estimate the stratum Y bar value, right? So if we have these, we can consider using separate method. Secondly, if each of the stratum size is large enough, then we can use separate methods. Let's say if each of the stratum, the sample size is so small, so that's making no sense of using separate method. Okay. Thirdly, assume the ratio estimator is unbiased for each of the strata. So this is a very strong assumption. Remember, we discussed about the ratio estimation. We need to make sure that they are linearly correlated for X and Y value, and they also need to pass through the origins so that we can use ratio estimation. So we need to make sure that ratio estimator is true, is unbiased for within each of the stratum, so we can use separate method. When do we use combined method? If we know the knowledge of the overall X bar, so we need to have the overall population true value of X bar, then we can use a constant R to multiply to that overall X bar to find my Y bar estimate under the combined method. Secondly, the sample size is not large enough. If they, like we just mentioned, if the sample size is so small, then we can combine them. We can rather go for a combined method, right? If the sample size is large enough, then we can use a separate method. Actually, the third point is the ratio estimation. If we use a combined method, if we observe each of the ratio within each of the between each of the stratum, they are quite similar, or they are linearly constant, then we can use a combined method. Okay,